Hello, everyone, and a very warm welcome to this lecture. My name is Professor Martin Hendry, and today I'll be talking to you about gravitational waves listening to Einstein's universe. I'm a professor at the University of Glasgow, and I'm also a member of the LIGO Scientific Collaboration. You can see it on my sweatshirt here. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And over the course of my talk, I'll be sharing with you what LIGO is and how we use these laser interferometers to detect some of the most extreme events in the cosmos, colliding black holes or exploding stars or even gravitational waves from the Big Bang itself. Gravitational waves are ripples in space-time predicted by Albert Einstein more than 100 years ago, and it's only in recent years that we've had the technology to be able to detect them. Now, this lecture is part of the 2024 Tyndall series of lectures for the Institute of Physics in Ireland, and I'm delighted and honoured to be giving this talk as part of the Tyndall series. John Tyndall was a famous Irish physicist who made important discoveries about carbon dioxide as a greenhouse gas, which is part of the key science that we need to understand if we're to do something about the climate emergency and climate change. So it's a very topical subject, and indeed it fits in with some of the very latest discoveries we're making in astrophysics in terms of Tyndall's appreciation that you had to measure things very precisely. Well, the LIGO interferometers I'm going to be talking about today are the most sensitive and precise scientific instruments ever built. So, as I said before, I'm a professor at the University of Glasgow. You can see some nice photos of the university campus here. I'm Professor of Gravitational Astrophysics and Cosmology. That's quite a mouthful. So what exactly does that mean? Well, gravitational astrophysics is about understanding how things work in the universe due to the interaction that we call gravity. We first learn about gravity probably through finding out about the discoveries of Isaac Newton, who thought of gravity as a force between massive bodies. Gravity is why the moon orbits the Earth or why the Earth orbits the sun, that sort of thing. So our understanding of gravity has evolved a lot over the last century. And that's largely down to the work of Albert Einstein, who helped give us a picture of gravity not as a force, but instead as a curving or warping of space-time. More on that in a few minutes. But when we talk about cosmology, what we're thinking about there is not the study of individual stars or planets or galaxies, but the properties of the whole universe. So what you see in my slide here on the right-hand side is an artist's impression of two black holes, perhaps the most extreme gravitational objects we can think about, just about to merge together. And I'll be talking about how we've discovered those through the gravitational waves, the ripples in space-time that they emit. And in the middle of the bottom panel, what we see there is an artist's impression of the history of the whole universe over 14 or so billion years since the universe began with what we call the Big Bang. So cosmology is concerned with addressing questions about the origin and evolution of the universe, how it began, how it got to look the way it does, what it might do in the future. I mentioned that I'm part of the LIGO Scientific Collaboration, or LSC, and LIGO is a laser interferometer gravitational wave observatory. So more on that in a few minutes. But before we talk about the science, it's useful just to think about what it means to be part of a large scientific collaboration. What you see in the right is a Google map showing all the institutions where LSC members work. There's a lot in the US, quite a lot in Europe, even some in Asia, Australia, and South America. So it's a truly global group of scientists and engineers, about 1,700 or so. And the bottom right-hand panel shows all the different institutions that are part of that LIGO scientific collaboration. In recent years, we've joined forces with two other groups of scientists in Virgo and Cagra to create a truly global team of scientists searching for gravitational waves. And this talk is all about how we do that and what we've learned about the universe. And here's Glasgow University where I work. It's quite an old building. It's a really splendid building. Some people think it looks a bit like Hogwarts from the Harry Potter stories. And this building was built in the middle of the 19th century. And at that time, the professor of physics in Glasgow then was William Thomson, Lord Kelvin, another famous Irish scientist. He was born 200 years ago in 1824 in Belfast. And he was professor of physics at the University of Glasgow for 53 years. This is a painting of him towards the end of his life. He looks a bit like Santa Claus with his long white beard. But he was appointed professor when he was only 22 years old, so a real whiz kid. But over the course of his career, he made many important contributions to science, to physics, to engineering, and to maths. He was really one of the most important scientists of the 19th century. A lot of the science that William Thomson studied was to do with everyday life. Things like, why does a hot cup of coffee get cold when you don't drink it, when you leave it in a room? Or indeed, why a glass of iced water gets warm. Why does the ice melt when you leave that in the same room? So Kelvin was all about understanding the physics of heat and energy and temperature. And that is really important for many practical applications in our everyday lives, like how fridges work, for example. One of the earliest designs of fridge was known as the Kelvinator. This was still some decades after Kelvin had died, but it was using a lot of the technology and the scientific ideas that he had worked on. So the company that made the fridge called it a Kelvinator. This is an advert from the 1950s. It looks a bit old-fashioned, but the basic design of a fridge today is just the same as it would have been then. Emphasizing that that same understanding of heat and energy and temperature is what underpins our understanding of climate change and environmental physics. So Kelvin's work is very important for how we might understand and do something about the climate emergency. Kelvin was also famous for making very precise scientific instruments. And that's a strong link to my theme of gravitational waves today, because as I mentioned earlier, the LIGO interferometers are the most precise and sensitive scientific instruments ever built. So these are some of Kelvin's designs from the 19th and very early 20th century. And, you know, they look a bit old-fashioned perhaps. These are actually marine compasses, but they were absolutely state-of-the-art for the time. So that's the images on the left-hand side are compasses that would have been used to navigate ships, commercial ships, and even Navy ships all around the world. And because of Kelvin's understanding of magnetism, he was able to design compasses that were more precise, more accurate than any had ever been before. Now, on the right-hand side, that's another one of Kelvin's instruments, and it looks a bit like a microscope. And that's not so far from the mark. It's actually what we call a mirror galvanometer. And it was a very precise instrument for measuring electrical current and electrical voltage, maybe a little bit like you might use at high school if you use an ammeter or a voltmeter. And Kelvin used this device for a discovery, for a project that really changed the world. What he was involved in was laying the first transatlantic telegraph cable. Here's a painting of the ship, the Great Eastern, which Kelvin was on board as it laid that cable across thousands of miles from one side of the Atlantic to the other. And you can see a little cross-section of the cable in the image on the left. So you can see there that it's just a few centimeters thick. Now, it was a very long way all the way across the Atlantic. You can see the path that the cable followed from the west of Ireland to Newfoundland in North America. And this created a big challenge because, well, the signal would get weaker as it traveled along the cable. So one solution to make sure you had a strong enough signal to reach the other end was to just make it really powerful to begin with, allowing for the fact that some of the signal strength would be lost. But that would make the cable have to be really heavy and thick and very, very expensive. So Kelvin's approach was to take a radically different angle to solve the problem. What he reasoned was that provided you had a sensitive enough measuring instrument at the other end, then you could afford to have a less powerful signal to begin with, which meant that your cable didn't have to be so expensive and so heavy and so thick. So he used his mirror galvanometer approach to create a super sensitive detector to measure those tiny electrical signals making their way all the way across the Atlantic. And that really did change the world because it suddenly brought both sides of the Atlantic so much closer together. Prior to that point, if you wanted to send a message from, say, Ireland to North America, you had to write a letter, send it by ship, and it would take days or even weeks to get there. With the telegraph cable, you could send messages more or less right away. So this brought the world together. It was as revolutionary for the 19th century as the internet, for example, has been in the 20th and 21st centuries. And this, together with his scientific contributions across many of the fields that we've mentioned, is why William Thomson was first made Sir William Thomson and then eventually Lord Kelvin, or Baron Kelvin of Largs. He was the first scientist to be made a lord in this way. And it's really important to learn from how Kelvin did things, that he wasn't just interested in finding out about fundamental scientific questions, but in turning them into practical applications. And in that sense, he was a real role model for scientists today, because many scientific projects are trying to answer fundamental questions about how the universe works. LIGO is very much like that, but we're also interested in developing new technologies and new techniques that can lead to useful spin-offs in our everyday lives. Now, Kelvin didn't get everything right. He died in 1907, and that was just 2 years after Albert Einstein first proposed his special theory of relativity. And then lots of other exciting developments happened in physics just after that, some of which we'll talk about a little later. But that means that Kelvin didn't benefit from the revolution that relativity brought in our understanding of energy. You might know that there's a famous equation to do with Einstein's theory called E equals mc squared. It basically says that associated with a small amount of matter, in principle, there's a huge amount of energy. We'll talk more about that in a moment. But because Kelvin didn't know about E equals mc squared, it meant that Kelvin didn't understand how the Earth could be so old. And he also didn't understand how the sun could supply as much energy as it does to the Earth and the other planets in the solar system for billions of years. We know all of this now, but back in Kelvin's day, when he tried to estimate the age of the Earth based on how much energy there could be in the sun, he concluded that the sun couldn't be any more than a few million, or maybe at the absolute most, about 100 million years old. And that was much younger than geologists and other scientists were saying the Earth had to be. So, as I said, Kelvin couldn't quite work that out because he didn't have the benefit of the revolution in our understanding of energy that came about with Einstein's special theory of relativity. So it's time to talk about Einstein now. This is a photograph of me sitting on a statue of Einstein in Washington, D.C. at the National Academy of Sciences. I like the statue very much as a kind of metaphor for my scientific career, because Einstein's a bit of a hero of mine, and I've worked in a lot of the areas of science and physics that Einstein revolutionized. Now, on the statue, there are some equations. Don't panic. This isn't a talk where we're going to get bogged down talking about lots of equations, but one of them you can maybe just about make out. It's the bottom of the three, and it's the one I've mentioned already, E equals mc squared. So in Einstein's special theory of relativity, published in 1905, he put forward the radical idea that space and time are relative to how we're moving, that our measurements of space and time will depend on how fast we're traveling with respect to another observer. And a consequence of this that Einstein published in another of his 1905 papers was the idea of the equivalence of energy and matter, E equals mc squared. So that says that even a small amount of matter m, like say 1 kilogram, contains in principle a vast amount of energy, because the c here is the speed of light. That's 3 times 10 to the 8 meters per second. So of course, if you square the speed of light, that's a colossally big number. And therefore, E, the amount of energy corresponding to that 1 kilogram of mass, is also huge. So Einstein took 10 years to go from his special theory of relativity to developing a general theory of relativity. In his general theory, what he wanted to do was not just talk about how space and time appear to an observer that's traveling very fast, but to look at how things behave when you're accelerating, when you're speeding up or slowing down. And it led Einstein to a very profound realization, a profound discovery, a connection between acceleration and gravity. In Einstein's picture of gravity, gravity is not a force like Newton had described several hundred years earlier. Instead, it's a warping or curving of space and time themselves. Now, a good picture for this, one that works well for me, is to think of a big sheet of rubber, like a huge trampoline, millions of kilometers across. And if you drop a planet onto that trampoline, like the Earth shown in this cartoon picture here, it will cause the trampoline to bend. And this is captured in a neat phrase due to another physicist, not Einstein, but another physicist called John Wheeler. He said that space-time tells matter how to move, and matter tells space-time how to curve. So the curvature of space-time determines how other matter will move in the vicinity of a massive body. So the reason, for example, that the moon orbits the Earth is not so much that it feels the force of gravity reaching out over 400,000 kilometers, but instead it's just experiencing the natural curvature, the warping of space-time caused by the gravity of the Earth. And it follows a circular path around the Earth for that reason. And similarly, matter tells space-time how to curve. It's the presence of matter in the universe in the shape of planets like the Earth or stars like the Sun that causes a warping or curving of space-time in the first place. So this is the key idea of Einstein's general theory of relativity, first published in 1915. We celebrated the centenary of that in 2015, 100 years later. And it's at that point that we made a remarkable discovery. Now, just before we get to that, let's think about that warping of space-time in the extreme. The most extreme conditions we can imagine is when space-time is curved so much that even light can't escape. And in that case, we would have a black hole, an object whose gravity is so intense that even light can't escape from it. It would appear to us as just a black region of space-time. So we're going to be talking about black holes a lot. That's our picture of what a black hole is. It's a region of space-time where the gravity is so extreme that even light cannot escape. And, well, we can study the universe in all forms of light, from gamma rays to radio waves, what we call the electromagnetic spectrum. But Einstein's general relativity, through predicting this warping and curving of space-time, also predicts another form of radiation altogether, not electromagnetic radiation, but gravitational radiation. And gravitational waves can give us a whole new way of studying the universe, a whole new window on the cosmos. So what exactly are gravitational waves? Well, let's think about that trampoline analogy again, the stretched sheet of rubber in which we had the Earth sitting, deforming or warping the fabric of space-time. Well, if you drop a heavy object onto a trampoline, the trampoline is going to wobble. It won't just bend, it will shake. So basically, gravitational waves are the wobbles or ripples in space-time caused by changing gravitational fields. Now, it's all very well to think of dropping a heavy object onto a sheet of rubber like a trampoline, but space-time is much stiffer than that. So in a sense, when you've got massive objects, like say my hand, which isn't particularly massive, and I'm not moving it very fast, yes, I'm changing its gravitational field, and therefore I'm producing ripples in space-time, gravitational waves. But we couldn't ever hope to measure them. What we've got to do is use the cosmos itself as our laboratory, and to have massive stars orbiting each other very, very fast, very close together, like in this cartoon. And what that will do is create ripples that spread out through the universe, the gravitational waves we're talking of. Now, to measure them is a real challenge, however, because just like ripples spreading in a pond, by the time those gravitational waves reach us, they're going to be incredibly weak. So to measure them, to detect the change in the curvature of our patch of space-time, requires making measurements corresponding to movements less than 1,000th the size of a proton, the subatomic particle in the heart of the nucleus of an atom. Or, To put it in more everyday terms, if you take one of the hairs in your head, we're trying to measure movements less than 1 million millionth the width of that hair. So how on earth are you going to make a measurement like that on the Earth? Well, on the Earth is the operative part of that because the Earth shakes. So it's a real challenge to measure these tiny, tiny measurements, not just because they're so small anyway, but because they could be swamped by effects that would make it so hard to detect that signal. And well, we can think of those other effects like the shaking of the Earth as noise. I called my talk Listening to Einstein's Universe, and we'll explore that idea in the next few slides because in fact, the signal we're trying to detect, if we think of that as like a sound, then the challenge we face is to detect that sound against a very noisy background. The way we do that is using laser interferometers, of which the LIGO observatories are 2 examples. There are others that we'll talk about a little later. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And these are L-shaped instruments. And using the 2 arms of the L, we can achieve the amazing sensitivity needed to detect the tiny changes in the shape of space-time caused by a passing gravitational wave. There are 2 LIGO detectors, and this was not buy one, get one free. These were very expensive projects for the National Science Foundation. But they are in Livingston, Louisiana, and Hanford, Washington, 3,000 kilometers apart in the US. And having 2 detectors was really important because that allowed a way to check whether what we were detecting was really coming from out there in the cosmos or was just a local disturbance here on Earth. So how exactly does a laser interferometer work? Well, what we do is use laser light as a precise measuring stick for the universe. We send the laser beam along 2 perpendicular arms, and as a gravitational wave passes by, it will stretch and squeeze space-time. So that's shown in the cartoon here, but of course it's enormously exaggerated. It's a really tiny effect. Remember, 1 million millionth the width of a hair, or equivalently about the width of a hair compared with the distance to the nearest star beyond our solar system, Alpha Centauri. So whichever way you think about it, it's a tiny, tiny signal we're trying to detect, but the laser beam can let us do that because what we do is we bounce the laser off the mirrors at the ends of the 4-kilometer arms. And in fact, we circulate the laser beam within the arms hundreds of times to effectively increase the path that they're traveling. And when the laser beams are then combined, what we can look for is a change in the pattern of what's called the interference between the 2 laser beams. The interference can be either constructive, when the peaks of the 2 laser beams line up with each other, or it can be destructive when we say that they're out of phase with each other and the peaks and the troughs will cancel each other out. Now, when a gravitational wave passes by, it stretches and squeezes space-time to change the path traveled by one laser beam compared with the other, and that will change the interference pattern that we see in the combined laser light when they're recombined again. So we can see that in the cartoon on the left-hand side. We can see that the overlapping of the 2 waves, the 2 laser beams, is changing as the gravitational wave passes by. And we would detect that as a change in the pattern of the light in the instrument when the 2 laser beams are combined. So what kind of signal would we be looking for? Well, what we see here is a graph. Scientists love to draw graphs, so let me walk you through this one. And it's showing how the distortion due to a passing gravitational wave would change over time as, for example, 2 black holes are orbiting each other and getting closer and closer together and disturbing space-time more and more and sending stronger and stronger ripples out through the universe. So that's shown in the little animation in the bottom left. We can see our 2 black holes spiraling in towards each other. We can see the gravitational waves spreading out, and the strength of that signal is increasing as the gravitational waves get closer together, as the black holes get closer together. But the black holes are also orbiting each other faster and faster. So what that does is it changes the frequency of the signal. So in the graph, you can see that the waviness The peaks are getting closer together. That means the frequency is increasing. And also the strength of the signal, that's the amplitude, is stretching out in the vertical direction. And when the two black holes collide, we get the maximum amplitude, and then space-time wobbles a little bit more, things settle down again, and the graph ends on the right-hand side. So this pattern, we can look at it, but we can also think of it as a pattern in sound waves, because it so happens that the frequencies of gravitational waves that our detectors are sensitive to, the ones on the ground, correspond to frequencies that our human ears can hear. So gravitational waves are not sound waves, but if we render them as sound waves, then as well as drawing a graph of the signal, we can also listen to the signal. And it sounds a bit like this. It rises in frequency, rises in pitch, gets louder, and then reaches a maximum and then fades away. So that's what we see in the graph. And we call this pattern a chirp. So that's basically what we're looking for, what we're listening for in these signals from the universe. But the challenge is, as we were saying before, there's a lot of background noise. There's a lot of sources of disturbance of the detector, which are nothing to do with colliding black holes out there in the universe, but they're to do with the ground shaking and other effects that can disturb the signal that we're trying to detect, indeed to swamp it altogether. So in 2010, the LIGO detectors began a process of being upgraded to advanced LIGO. And this was a project that the UK, led by the University of Glasgow, played a significant role in. Because what we wanted to do was to reduce that background noise so that the detectors were more able to listen to signals coming from the universe. So one of the key ways that that was done was to improve the sensitivity of the mirrors at either ends of the L-shaped arms. The laser beams are bounced back and forth from those mirrors. And what was done was to suspend the mirrors not by steel wires, which initially LIGO had used, but to replace those steel wires with incredibly delicate silica fibers, glass fibers. And these shake less in the kinds of conditions that the LIGO detectors would experience. So consequently, it's like reducing the amount of background noise, because you don't want the mirror shaking because of that. You want it moving because of the stretching of the arms of the detector caused by a passing gravitational wave. So in 2015, the two LIGO detectors were upgraded to what we call advanced LIGO. Let me just pause this for a moment, because what I'm going to play is the signal that we detected on September 14th, 2015, just a very short time after the LIGO detectors had been fully upgraded to advanced LIGO with this more sensitive instrumentation inside. So on September 14th of that year, this is the signal that we detected. So we see it as a graph, but we'll also listen to it. So let me freeze it there and we'll talk you through what's going on. So firstly, I'm playing it over and over again, which makes it hopefully a little bit easier to work out what's going on. But with the real signal, it was over and done with in just a small fraction of a second as the gravitational wave passed by the Earth and swept on through the universe. But by playing it over and over again, it's just giving our ear and our eyes time to get accustomed to what's going on. So what we see, maybe what we hear, is that chirp-like sound. We hear a hiss of the background noise, but then we also hear the zoop, the sound of, well, we'll see in a moment what it actually was that produced this signal, but it's very similar to that pattern that we saw in the theoretical prediction from a few slides back. So this signal, to make it a little bit easier for us to hear, I've shifted it to slightly higher frequencies. Whereas if you play it in the original form, it sounds a bit more like a kind of dull thud, much lower frequencies, lower pitch. But when you move it to higher frequencies, it's a little bit easier to hear. So let me play it a few more times so you can get the hang of what's going on. So the thing to notice, let's just go back to that one last time. The thing to notice is how similar the pattern appears in LIGO Hanford and LIGO Livingston. Let's advance the video and freeze it. There we go. So remember, these detectors are 3,000 kilometers apart. So it was already very notable that the signal appeared to be so similar. When they're that far apart, it immediately makes it less likely that this could be some kind of ground-based effect, some kind of noise associated with the detectors themselves. Because why would it be that the pattern looks so similar when they're so far apart from each other? But it took us a number of months to very carefully analyze all of these data and to convince ourselves that we weren't just seeing noise in the detectors, that in fact we were observing gravitational waves coming from deep in the universe. And we announced that in February 2060, about 5 months later. And this was about 100 years after Einstein's prediction that gravitational waves existed. So what exactly had we detected? Well, here's the data again. Again, notice that the blue and the red, they overlap very well. So the similarity of the two signals detected 3,000 kilometers apart was a real telltale sign that we were onto something here. And by very careful analysis of the data, we could work out that what we were seeing or hearing was the gravitational waves produced from the in-spiral and merger of two black holes about 30 times the mass of the sun and more than 1 billion light years away. Now, working out the masses of the black holes and how far away the signal is coming from, that's quite tricky. It requires a lot of very careful analysis of the data. And I'm going to play a short video narrated by a colleague, Laura Nuttall, from the Institute of Cosmology and Gravitation at the University of Portsmouth, that explains a little bit how we do that.
On the 14th of September 2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
So I said that the signal came from more than 1 billion light years away. This really is like it says in Star Wars. We're detecting something that happened a long time ago in a galaxy far, far away. Those gravitational waves had been spreading out through the universe for more than 1 billion years, just waiting to pass through our LIGO detectors and be detected as this chirp-like signal. So this was a huge deal. It was covered in hundreds of newspapers around the world. It was a real verification of the last piece of Einstein's general theory of relativity. It was a huge scientific deal. So here's an animation that we showed at the press conference to announce that discovery in February 2016. So you can see the warping of space-time produced by the two black holes. And then as they merge together, we get that spike of gravitational radiation given off. And then what you've got after that is just a single dimple in space-time produced by the single merged black hole. And space-time wobbles a little bit more, then things settle down. And all of that unfolds in just a fraction of a second, maybe about 1/3 of a second. So I mentioned before that these two black holes had masses of about 30 times the mass of the sun. We could measure their masses quite precisely. We found that one had a mass of 29 times the mass of the sun, and the other 36 times the mass of the sun. The sun has got a mass of about 2 million kilograms. So these are very massive black holes. But the final black hole that we see on screen now, it had a mass of 62 times the mass of the sun. So in just about 1/3 of a second, the equivalent of 3 times the mass of the sun had been converted into gravitational wave energy. And that's an amount of energy that we can work out using Einstein's E equals mc squared, because the amount of mass is 6 million kilograms, 3 times the sun's mass, multiply that by the speed of light squared, that's how many joules of energy were produced in gravitational waves. And since all of that happened in about a third of a second, we can also turn that into an estimate of the gravitational wave power, which is energy divided by time. And all of this probably happened without any light being given off at all, because gravitational waves are not electromagnetic radiation, they're a different form of radiation altogether. So in a real sense, we're probing the dark side of the universe. And the number that we get when we work out the gravitational wave power is quite mind-blowing. We could calculate that it was perhaps about 50 times greater than the combined light power, what we call the luminosity, of every star in every galaxy in the entire universe, released in that short burst of gravitational wave power. Now, I think it was Darth Vader that said you should never underestimate the power of the dark side. And I hope that little calculation we've just done proves that Darth Vader was right. Well, I'm not going to argue with him anyway. We really are tapping into a colossal gravitational wave power, sort of locked up in the fabric of space-time, just waiting to be released when something as extreme as 2 black holes colliding occurs out there in the universe. So this was a big deal. It was awarded, that discovery of gravitational waves with the LIGO detectors, the 2017 Nobel Prize in Physics. And indeed, our colleagues in the Virgo collaboration shared in that prize because they contributed to the analysis back then in 2015 when that first detector discovery was made. But the actual prize itself went to 3 senior colleagues in the LIGO collaboration, Ray Weiss, Barry Barish, and Kip Thorne, shown here. But in 2017, the Virgo collaboration moved to a whole new level of cooperation with LIGO, because not only were they involved in analysing our data from the LIGO detectors, but Virgo began operating as well. In 2017, the Virgo interferometer was upgraded to Advanced Virgo, using many of the same techniques to improve its sensitivity that had occurred for Advanced LIGO, and that began operation on August 1st, 2017. Now, this was a real game changer, because with 3 interferometers, we could pinpoint where in the sky the gravitational waves had came from much more precisely. The way it works is this. If you've only got 2 interferometers operating, you can still get some information about where the gravitational waves came from the arrival time of the signal at the 2 detectors. So with LIGO Livingston and LIGO Hanford, for example, that very first signal that we detected in September 2015 arrived 7 milliseconds apart between the 2 detectors, 3,000 kilometers apart in the US. And from knowing the speed of light, because according to Einstein, gravitational waves travel at the speed of light, then we can work out where in the sky the signal came from. It uses a lot of the trigonometry that you learn in maths in high school, all those sines and cosines and tangents. But you can't determine exactly where in the sky with only 2 detectors, because there's a ring of places on the sky where the signal could have came from. So that's shown in this cartoon on the left here as the red ring on the sky. But adding Virgo into the mix gave us 3 pairs of detectors, and hence 3 rings on the sky where you could look at the timing differences between any 2 of them. And where those 3 rings overlap, well, that's where your signal came from. So after Advanced Virgo joined our network on August 1st, 2017, it only took about 2 weeks before this additional detector really paid off. We detected a pair of black holes colliding on the 14th of August 2017, and the sky localization from that source was way better than the signals that had been detected prior to that, including the very first one that we've been talking about earlier. 1509-14, 14th of September 2015, that first detection, we could only pinpoint its location on the sky to about 900 square degrees. But when it came to the 14th of August 2017, we could pinpoint the location to more like 60 square degrees, more than 10 times better. And then 3 days later, there was another remarkable discovery, again benefiting from Virgo being part of our global network. Because On that day, we discovered another gravitational wave source, but this time not from two black holes colliding, but two neutron stars colliding. So what exactly is a neutron star? Well, stars of different mass undergo their evolution in somewhat different ways. If you have a small star like the sun, it may evolve into a red giant. We think that might happen to our sun in a few billion years. And then that red giant becomes a beautiful object called a planetary nebula with a very dense object called a white dwarf at its center. A white dwarf has got the mass of about the sun, but it's only about the size of the Earth, so it's very dense. On the other hand, if you have a larger star, then it will become a red supergiant and undergoes a more violent end state, an explosion that we call a supernova, leaving behind either a black hole that we've talked about before, or possibly a neutron star. If the star is more massive, you'll get a black hole. If it's somewhat less massive, you'll get a neutron star. A neutron star is maybe about 1.5 times the mass of the sun, but only about the size of a city, about 10 kilometers or so across. The very first neutron star was detected by another famous Irish astronomer called Jocelyn Bell in 1967. She detected it using a radio telescope because this was a rapidly spinning neutron star, giving rapid pulses of radio waves as it spanned past, a bit like the beam of a lighthouse as a lighthouse rotates, as the lamp of the lighthouse rotates. So this was a truly remarkable object. A neutron star, as I said, perhaps only about the size of a city like Manhattan, but weighing 1.5 times the mass of the sun. So that means it's an incredibly dense object. Even a centimeter cubed of neutron star would weigh billions of tons. And if you have two neutron stars colliding with each other, that's going to shake up space-time a great deal. It's going to produce gravitational waves. And that is what we detected on August 17th, 2017. But even more important, it wasn't just detected in gravitational waves. This colliding neutron star event was observed in electromagnetic radiation, first in gamma rays from a NASA satellite called Fermi and a European satellite called Integral. And then it was observed in other telescopes across the whole electromagnetic spectrum. So let's have a look at the signal, and indeed let's have a listen to the signal. It's another chirp, but it stretches out over much longer this time, just like Laura's little cartoon video was describing some slides back. So what we've got is that chirp-like signal unfolding, and then about 1.7 seconds after the two neutron stars merged, there was a ping due to the arrival of an intense burst of gamma rays coming from what we call a gamma ray burst. And because LIGO Livingston, LIGO Hanford, and Virgo were all operating, that allowed us to pin down the location of this gravitational wave source quite precisely to, again, about 60 or less square degrees. And that meant that we could see that it overlapped with where the gamma rays were coming from. And even more importantly, we realized that there was only, a few dozen galaxies within that patch of sky. So it was possible for astronomers using optical telescopes to go take a look at those galaxies and see if there was anything that had gone boom. And sure enough, in this little galaxy here, NGC 4993, we discovered that gamma ray burst that I mentioned before. So here's an artist's impression of it. We discovered the remnant of that gamma ray burst, an object that we call a kilonova. So what we see here is the shaking up of space-time from the gravitational waves, the collision of the two neutron stars, and two intense beams of gamma rays, which were seen by Fermi and Integral. And then what we see here is a before and after photo of that galaxy 4993. We can see the red arrow pointing towards a new star that's been formed in that galaxy that wasn't there before. So on August 17th, 2017, this new star is the leftover remnant of the collision of these two neutron stars. Now, there's a huge amount of fascinating science has emerged from studying that kilonova object, that remnant of the neutron star collision. But one of the aspects that's been of great interest to us is using that neutron star collision and measuring the distance from the gravitational wave signal to get a new measurement of how fast our universe is expanding. That's a very important number for cosmology, but it's a number that we still don't know as precisely as we would like. And in fact, in recent years, there's been some rather puzzling measurements made by different methods that don't agree with each other. So our great hope is that gravitational waves will be able to help settle that tension between different values of what we call the Hubble constant, the expansion rate of the universe. So looking ahead now to what we've been doing since 2017, our first stop on that discussion is our third observing run. So that began in 2019 after the detectors had been upgraded to make them even more sensitive. And that ran for nearly a year until March 2020. Now, during that time, what we were doing then, when we had a candidate gravitational wave event, was we were putting out a public alert on the internet to say, hey, we think we've maybe detected something. There was an app called Chirp, for example, created by our colleagues at the University of Birmingham, which could inform you, could let you know that there was a candidate event, of where maybe it was in the sky, some of the properties of the event that we thought we had detected. So over the course of our third observing run that ran through to March 2020, the number of detections that we made really climbed. That's because our instruments were even more sensitive. So in the first two observing runs up to August 2017, we'd seen a total of 11 gravitational wave events. And then over our third observing run, April 2019 through to March 2020, the total number of detections rose to 90. So we're seeing gravitational wave events during that period every few days. And there's a very rich variety of types of discovery that we made. They were all either black holes colliding with black holes, neutron stars colliding with neutron stars, or some examples of a neutron star and a black hole colliding together. So let's talk you through some of the things that we've learned. So we found examples of two black holes colliding where the bigger one was much bigger than the smaller one. That's like what's being shown in this cartoon here. And that's an example where you get a much richer detail in the gravitational wave signal. You get what are called extra harmonics, a bit like the harmonics in a musical note or a musical chord made of several notes. So signals like that can give us more information about the masses, about the ways that black holes are spinning, things like that. We actually also detected in our third observing run another event where there was a much bigger black hole than the smaller object. And we weren't quite sure if the smaller object was either a really massive neutron star or a not very massive black hole. We think it's more likely to have been a black hole, but we weren't sure. That was in August 2019. But in May 2019, a few months before, we detected a pair of black holes colliding that were really very massive indeed. The black hole that they left behind was about 150 times the mass of the sun. That puts it in a range that we call an intermediate mass black hole. We know about supermassive black holes. We're pretty sure that almost every galaxy has got one of those lurking at the center. And the masses of those is perhaps somewhere around 1 million or even up to 1 billion times the mass of the sun. So how do you make a supermassive black hole? Well, a reasonable way to think about that would be that it's built up out of smaller mass black holes. And maybe this intermediate mass black hole is part of that story. It might be that the discovery of 1905-21 is actually the result of a chain of black holes merging. So we're seeing the final part of that chain, but perhaps what happened sometime before was two pairs of black holes merging first with each other, and then each emerged remnant from that pair merging in turn to give our black hole of about 150 times the mass of the sun. And then at the other end, we did see another pair of neutron stars merging. So these are much lighter, more like just 1 or 2 times the mass of the sun. But this time we didn't see an accompanying gamma ray burst or other forms of electromagnetic radiation. So an artist's impression of that neutron star merger is shown in the bottom right here. It could just be that that was too far away and too poorly localized on the sky to allow us to have caught the EM counterpart. So we got very lucky in August 2017 when we saw that binary neutron star and saw the gamma rays and all the electromagnetic radiation. but nonetheless, looking for the EM counterpart of a binary neutron star merger is going to be very important in the coming years as well. And in January 2020, just before the end of our third run, we saw two events about 10 days apart, which this time really were examples of a black hole and a neutron star. Our best guess is that this was definitely a black hole as the larger object, and almost certainly a neutron star as the lighter object. So here are some computer simulations of the gravitational waves given off by events like this. So in the top one, what we're seeing is, when we zoom in a little bit, is that rich pattern of harmonics again, like we talked about before. But in the inset, you can see the neutron star, this sort of orange blob, orbiting the black hole. And in a moment, it's going to be swallowed more or less whole. It's going to be swallowed in one gulp by the black hole. Whereas in the bottom animation, what we've got going on there is a neutron star orbiting a black hole, but kind of being torn apart by the gravity of the black hole. And, well, in that case, you would expect to see some electromagnetic radiation given off as the neutron star is ripped apart by the black hole's intense gravity. So the two neutron star black hole mergers that we detected early in 2020 were much more, we think, like the top animation than the bottom animation, in the sense that we didn't see any electromagnetic radiation given off, and we didn't see any strong evidence for that being torn apart effect that we saw in the lower animation. So in a sense, what that means is that the black holes for these two examples were much more like Pac-Man than Cookie Monster. The black holes were swallowing the neutron stars in one gulp rather than being a mesa eater like Cookie Monster is. But nonetheless, finding examples where neutron stars are shredded in that way, where the black hole is a mesa eater, would be hugely valuable. It would tell us a bit more about the origin story for these neutron star black hole systems, but it would also offer us the opportunity to learn something about the physics going on inside neutron stars themselves. And since those are incredibly extreme conditions, with densities billions of times greater than anything we can replicate in the lab here on Earth, that would be a window into really fascinating areas of fundamental physics that would hopefully really enhance our understanding of what's going on with nuclear matter. So I'm nearly at the end of my talk. This is a slide which summarizes all the 90 detections that we made during that first and second part of the third observing run. So this was published a couple of years ago, and right now is already giving astronomers and physicists around the world lots of opportunity to study those data and learn about black holes and neutron stars, and to learn about gravitational waves. And here's a little animation showing some of those systems that we detected. So there's one or two neutron stars in there as well, but most of them are black holes, but of very different sizes. So they're orbiting at different rates, and the black holes and neutron stars have very different masses. But we haven't stopped there. Our fourth observing run began on May 24th, 2023, and the second part of our fourth observing run is just about to begin in April 2024. The first part of 04 gave us another 80 or so candidate gravitational wave events, adding to the 90 that we had already published from our first three observing runs. So we haven't yet published results from those 04A candidates, but nonetheless, they show a strong continuation of the trend to observe more and more gravitational wave events. And the more we observe, the more we'll build up a picture of how the population of gravitational wave sources fits into our understanding of fundamental physics and cosmology. So we're expecting over the next few years to overall get a 2 or 3 times increase in our event rate through to our fifth observing run, 05, that will take us towards the end of the 2020s. So by the end of that, we really will be looking at many hundreds of gravitational wave sources. But we're not stopping there. As we go through to 05 and the end of the 2020s and into the 2030s, we're looking to have a network of detectors operating around the world, LIGO Hanford and Livingston and Virgo, but also a new LIGO detector in India, and another detector, Kagra, in Japan. The more detectors we have, the more precisely we can determine the sky position of a gravitational wave source. And looking into the 2030s, moving even deeper into the universe, we're already planning a third generation of detectors beyond initial LIGO and advanced LIGO, what we're calling the Einstein telescope in Europe and the Cosmic Explorer telescope in the US. With the current second generation of detectors, we're only probing a small part of the universe, kind of roughly contained within that yellow circle. But we want to look even further back, even longer ago, to galaxies further and further away, to where gravitational waves are being emitted from perhaps some of the very first galaxies after they began to form in the early universe. And plans for those third generation detectors like the Einstein telescope are developing rapidly. Here's an artist's impression of the Einstein telescope, which will be built in Europe probably in the mid-2030s, and in fact will be underground, which helps to mitigate some of those sources of noise that we talked about earlier. And then, just like the electromagnetic radiation that we study in astronomy exists as part of a spectrum, all the way from radio waves to gamma rays, in the same way, gravitational waves have a spectrum as well. And all that I've really talked about so far has been high-frequency gravitational waves that we can detect using ground-based interferometers. But if we want to detect lower-frequency gravitational waves, we can't do that on the ground because the Earth just shakes too much. The noise would be too great. So what we have to do is build gravitational wave detectors and put them into space. And there's going to be just such a project called LISA, the Laser Interferometer Space Antenna. It's led by the European Space Agency with significant contributions from NASA, and it was approved as the next big ESA mission in late January with a target launch date of the mid-2030s. So looking ahead to next decade, our picture of the universe with gravitational waves will get even deeper and richer as we build ever more sensitive ground-based detectors and as we also take gravitational wave detection into space. So I hope you've enjoyed this lecture, this talk, which has given a sense of where we are in this exciting new field of gravitational wave astrophysics. It involves incredibly precise measurements, which links us back to the precise measurements made by John Tyndall and indeed Lord Kelvin, William Thomson, all those decades ago as pioneering physicists from the 19th century. But I hope what I've shared with you gives a picture of gravitational wave astrophysics as very much science for the 21st century. And I think this field has a very bright future. And I hope everyone watching too, by studying STEM subjects, by studying physics and science at high school and beyond, will also have a very bright future indeed. May the force be with you.